Chapter 3.2 Series and Parallel Circuits. By the end of this section, you should be able to calculate currents, voltages and resistances in series and parallel circuits. We will see what series and parallel circuits are. Derive the equations for combining resistances in series and parallel circuits. Let's see the details now. You should know the meanings of certain words, and they are also given at the end of each subchapter or end of each part. You can see now this is 3.1 part 1. And here you don't get anything at the bottom, but in most of these subchapters you can see like this the definitions are given. Okay, the fundamental rules governing measurements in electrical circuits are the conservation of charge and conservation of energy. So this is where we will later see in part 2 Kirchhoff's first law and second law. Kirchhoff's first law is the law of conservation of charge being used, and in the second law we use the law of conservation of energy. We will see the details. These determine how currents, voltages and resistances changed around any particular circuit. You learned that energy cannot be created or destroyed, but it can be transferred from one form to another. Then current, the total amount of charge within a circuit, cannot increase or decrease when the circuit is functioning. So that means if you consider this circuit over here, the total charge in this circuit is a constant. The charge cannot disappear. Like energy cannot be created or destroyed, charge also cannot disappear, or it cannot be created within this circuit. So the total amount of charge within a circuit cannot increase or decrease when the circuit is functioning. Currents are measures of charge flow through a component, so they must be measured in the same line as the component. That is, the ammeter must always be placed in series next to the component. We use a device called the ammeter to measure current. You would have learned that in the O-level or IGCSE 9-1 classes as well. Ammeter is used to measure the current, and it is connected in series with the component that you want to measure the amount of current that is flowing through that component for. So if you want to find the amount of current flowing through this lamp or bulb, you have to connect the ammeter in series with that lamp or bulb, so that whatever current that flows through the lamp is also the same as that flowing through the ammeter, because there is no other alternative path for the current to flow. Now this is a cell. The current flows out from the positive terminal and goes through this ammeter. Now you can see there is no other way for the current to flow, so it has to flow through the lamp and then going like this and back through the cell. So the two components, ammeter and the lamp, are in series, because whatever current flows through this has to flow through this. There is no other path, so they are in the same path that the current flows. So that's how we know that they are in series. Currents in series circuits, all these components you can see here are in series. How do we know that they are in series? Because whatever current that flows through the cell is flowing through each of these components, and there is no other alternative path for them to flow. Any group of components that follow in series in a circuit with no junctions, okay, or junctions, or we can also say other paths or routes. In physics, for circuits, we use the word junction. So there is no junction, or if you learn the American syllabus, the word used is nodes, N-O-D-E-S. The British people use the word junction. So there is no junction, path, node, alternative path, route for the current to flow. Whatever current flows through any of these components is the same current flowing through the other components as well, because there is no other alternative path or junctions in the circuit. With no junctions in the circuit, must have the same current through them all. So this is how you know that the components are connected in series. So you can see the ammeter reads the current as 1 ampere. This ammeter, which is connected here between the lamp and the resistor, is also reading 1 ampere. Then this ammeter, which is connected between this resistor and the cell, also reads 1 ampere. So all these ammeters read 1 ampere because there is only one path or one way for the current to flow. the current is constant through a series loop in a circuit. This is, by the way, called a loop. You can see it's a loop. This is a loop. Currents in parallel circuits. Now, when components are in parallel, they will have the same potential difference or voltage across them. You have learned that the scientific term for voltage is potential difference. So the potential difference between these 2 points and these 2 points are the same because they are in parallel. So we will see whenever a circuit encounters a junction, whenever current encounters a junction in a circuit. Now you can see here, this is a three-way junction. 1, 2, 3. Three-way junction, like in the roads also we have junctions, 2-way, 3. We don't have 2-way, right? 3-way, 4-way junction. Here it's a 3-way junction. Whenever a current encounters a junction, the charges can only go one way or the other. So the current must split. Now, for example, you see here, 1 ampere comes this way, 2 amperes come this way, then the two currents add up and go this way. So you get 3 amperes. So the sum of currents entering a junction should be equal to the sum of currents leaving the same junction. This is what we call Kirchhoff's first law. You will see that in part 2 in the next video. The proportions that travel along each possible path will be in inverse proportion to the resistance along the path. So always the current tries to flow through the higher amount of current tries to flow through the less resistance path. Now if these lamps are identical, let's say they have the same resistance, here then the resistance will be in this branch, in this path, the resistance will be double the resistance here in this branch or path. We call these branches. Okay, so from here to here it's one branch, then from here all the way to there, that is another branch. So you have one branch here, another branch here, and another branch here. Now the current that is coming this way, which is 3 amperes, will divide such that more current flows through the less resistance path. Now here it is one lamp, so the resistance here between this point and this point or in this branch is half the resistance in this branch. So double the current will flow through this branch compared to this branch. So you can see here it's 1 ampere, here it's double, 2 amperes. Here the resistance is, let's say, R. Here, because there are two identical lamps, it will be 2R. We have to assume that all 3 lamps have the same resistance. I think they mention it also here. Currents split at circuit junctions, but the total current will remain the same in order to conserve charge. Current is charge divided by time. It is the rate of flow of charge. So in a certain period of time you have a certain amount of charge coming this way. Now you can see it's 3 amperes, which is 3 coulombs per second. So 3 coulombs are entering this junction. You can see the black dot indicates the junction. 3 coulombs every second is entering this junction, and this way you can see it's 2 amperes. So 2 coulombs are leaving every second. Here 1 coulomb is leaving every second. So for the second, here this way 3 amperes, 2 amperes, 1 ampere. So you can see 2 plus 1, 3. So that's what that means. The total current entering a junction should be equal to total current leaving a junction, because the charge has to be conserved. The proportions that travel along each path will be in inverse proportion to the resistance along the path. I already explained that. If the path has high resistance, the current is less likely to go that way. However, the total along the branches must add up to the original total current. So you can think of it like this. You can think that a high resistance path, like what you see here, is a path, let's say, where there is a lot of potholes on the road. Now you can imagine that these charges are like cars and these wires are like roads. Now more vehicles will try to flow through take the road which is better, which has less potholes, which is maybe carpeted. You can think of the highway as a very low resistance branch or road. So always the cars, when we are driving, we try to take the least the best road. Okay, we try to take the best road. So similarly, the less resistance path, you can imagine, is analogous to a better road. More resistance in that branch means it's like a road that is with a lot of potholes, a lot of bumps, the road is not even, something like that. Then we have voltages around circuits. The instrument that we use to measure the voltage or potential difference is called a voltmeter. You would have seen this in the O-level class as well. This is the symbol for voltmeter. It's a circle with a capital V inside it. The symbol for ammeter is a circle with a capital A inside it. Voltmeters must always be in parallel across the components they are measuring. You can see the voltmeter is connected in parallel with this lamp here. Now this lamp here is in parallel with these two lamps which are in series. These two lamps, you can see whatever current flows through this, which is 1 ampere, has to flow through this because there is no alternative path from here all the way to here. So these two lamps, this lamp and this lamp, this is the symbol for a lamp, by the way, also called bulb. These two lamps are in series, but if you consider from here to here, these two lamps which are in series together are in parallel with this lamp here in this branch, and also it is in parallel with this cell here. This is the symbol for a cell, and this lamp here is also in parallel with this cell here. Voltages are measures of energy change as charge passes through a component. Now what is happening is the battery or cell or power supply, it can be a dynamo, it can be a generator, they give energy to the chargers. So the chargers gain electrical energy from the power supply. The power supply can be a cell. If it's a dry cell, for example, chemical energy is converted to electrical energy in the cell. So these electric charges are pushed through the circuit by the power supply. So the battery, the dynamo, the generator, the cell acts like a battery acts like a pump for the chargers. So it gives energy to the chargers and pushes them around the circuit. Now what happens here is the power supply, in this case it's a cell, gives energy, electrical energy to the chargers. And what happens over here is, over here and over here, which are the electrical components using the electrical energy, the energy of those chargers is being used up. It is converted from electrical energy to other forms of energy. For example, light energy. The lamp also gets heated, so part of it also is converted to or transferred to heat energy or thermal energy. Now the power supply converts other forms of energy to electrical energy. In the case of a battery or cell, it converts chemical energy to electrical energy. In the case of a dynamo, it converts kinetic energy to electrical energy. In the case of a generator also, kinetic energy is converted to electrical energy. So power supplies give energy to the electrons or chargers. In this circuit, the charge carriers are the electrons. But at the other components, the electrical energy of those electrons or charges is being used up. It is converted to or transferred to other forms of energy like heat energy and light energy here. Voltages are measures of energy change as a charge passes through a component. So they must be measured from one side to the other, because the charges lose energy when they pass through this. So on this side it has energy. For example, let's say here it has energy, it's not being used up, but once it comes to this side, that energy has been used up. So let's say it's 2 volts. You have learned the equation for potential difference of voltage. We learned that V is equal to W over Q. V is equal to W over Q. Okay, now this has the unit of voltage is volts, EMF for even potential difference, it has the unit volts, and work done is energy transferred. So E, we can replace the W with E because work done is energy transferred. It will be E divided by Q. So here the unit will be joules per coulomb. So for every coulomb of charge, the amount of energy that is either given or used up is the number of volts. Now in the case of a power supply, the energy is joules of a certain amount of energy is given to each coulomb of charge. Now for example, if you take the cell, that is, let's say what we have here, we have a lamp and then something. Okay, let's just take one lamp for now. Let's say the EMF of this is 1.5 volts. So what is happening is, for every coulomb of charge, for every coulomb of 1.5 coulombs of for every coulomb of charge, 1.5 joules of energy is given over here. 1.5 joules of electrical energy is given to each coulomb of charge at the cell. But over here what happens is, at the lamp uses the electrical energy. So what happens is 1.5 joules of energy is being used up here for every coulomb that is passing through this lamp. So here the energy is used up. Here the energy is given by the cell to the electrons or coulombs of charge. That's why the battery dies out in the end. The battery will lose its chemical potential energy, and in the end the battery will be dead, because when it is in a circuit like this, the energy that is converted here to light energy and maybe thermal energy is coming from the battery. So here also it will be 1.5 volts, because you can see here, if you consider, let's say, this point and this point, you can see they are in parallel. That way we can say here and here, you can see they are in. So that's why the voltage here, the potential difference across this lamp is also 1.5 volts. We can say the EMF of the cell is 1.5, then the potential difference V. Remember, we can use EMF only for power supplies. We can't use the word EMF for components that are using electrical energy. EMF is used only for power supplies. Potential difference, voltage, is used for components that are using the electrical energy. We can even use the word potential difference for the voltage across the battery as well, but the more correct term is EMF. Now you will see the difference between EMF and potential difference across the battery, which we call terminal potential difference, later on. It's in another subchapter here. So we are still in part 1, but I think it's in part 3 that you will see the details of internal resistance. There you will have the difference between EMF and terminal potential difference, which is the potential difference between the terminals of a cell or battery. That's why we call it terminal potential difference. Okay. So you can see these two components are in parallel because it's connected across. If you connect it across like this, that means the two components are in parallel. The potential difference across them will be the same. Then voltages in series circuits. Any group of EMFs that follow in series in a circuit with no junctions in the circuit will have a total EMF that is the sum of the individual values. Now what that means is, if we have just one like this, that means it's a cell. So just one symbol, line and a short line. This is the positive terminal, this is the negative terminal. In general, what this means is it's a cell. A collection of cells or a number of cells form a battery. Now, if you have just this symbol alone, generally we take it to be 1.5 volts, because if you look at a cell, even the word battery is used for cell, it is 1.5 volts. If you have two of them connected like this with opposite terminals facing each other, the EMFs add up. Now here this is 1.5, this is also 1.5, so total EMF will be 3 volts. Here you can see 3 of them are connected with opposite terminals facing each other, so we add them. Now the problem here is, so this is 4.5. Now the problem in this last diagram is 1 is connected the other way around. What that means is, you can see the positive terminal here and the positive terminal here are facing each other. So if all of them have a EMF of 1.5 volts, these two will cancel out. So this is 1.5, this is minus 1.5, these two cancel out on this side, but this and this, they add up. This is 1.5, this is also 1.5, opposite terminals are facing each other, so here it will be 3 volts. So the total will be 3.0 volts, and that is what is explained here. With no junctions in the circuit, we'll have a total EMF that is the sum of the individual values, accounting for the direction of their positive and negative sides. For example, two 1.5 cells in a TV remote control will be in series. Now, if you take any electrical device that is using batteries, we always place the batteries so that the opposite terminals are facing each other in that circuit. So the total EMF will therefore be the sum of the individual EMFs of those cells. If you connect one the other way around, if they have exactly the same EMF, then you will see it doesn't work because it is cancelling each other out. Positive and negative. For example, two 1.5 cells in a TV remote control will be in series, so they supply an EMF of 3.0 volts. This is also true for any string of potential differences in series. So you see here, in series, EMFs in series will add up. Take care to account for their direction. As cells in opposite directions, that means opposite terminals facing each other, oppose each other and cancel out the EMFs, they would wait. Okay, so this is not terminals. Okay, so as cells in opposite direction means the cell is connected so that the same terminals are facing each other. So for example, if you take a battery or cell, you know, this side is positive, this side is negative. You can see it, it's shown on this battery. Okay, then if you connect it like this, another one like this, they should be touching each other. Okay, so then what will happen is, so these two are touching, then what will happen is, if both of them are 1.5, then positive and positive are facing each other. So this, if I draw it in symbols, it will be something like this. Okay, so this is this cell and the other one is this one. Okay, so positive and positive are facing each other, negatives on this side. So if each one was 1.5, then 1.5, the other one is connected the other way, so that will be plus minus 1.5, which is 0 volts. Okay, so as cells in opposite directions oppose each other and cancel out the EMFs they would supply. So what that means is this. Okay, the same terminals are facing each other. Positive and positive, if they face, they cancel out. Positive and negative face, they add up. Face each other, they add up. Potential differences in series will add up. So here you can see this is a battery. This dashed line indicates that there is a number of cells from here to here. So we can say maybe, you know, if each of these is 1.5, then 1.5 times 4 will give you 6 volts. So we can say 6 of these are connected from here all the way to here. And we don't need to draw all that, simply we can use a dashed line like this to show that there is a number of cells in between these two. This is the symbol for a battery. Even this, they are also the symbols for batteries because you have a number of cells. This, strictly speaking, is not the symbol for a battery, it's the symbol for a cell. Okay, potential differences in series will add up. What would be the total potential difference across the two resistors in this diagram? Now, for there to be a potential difference, there has to be a resistance between those 2 points. So if you are measuring the potential difference from here, this point and this point, as you can see, this voltmeter is connected between this point and this point. So for there to be a potential difference between those 2 points, there has to be a resistance between those 2 points. and in this case the resistance is 10 ohms. So that will cause the potential to drop. Now on this side the potential is 6 volts, anywhere from here all the way to here, because now there is no potential difference across the ammeter, because ammeter has a negligible or zero resistance, we can assume. So if there is no resistance, now even a wire has a negligible or zero resistance. There is a resistance in the wire, but we assume it's negligible or almost zero, so we take it to be zero. Now if you connect a voltmeter between this point and this point, since there is a negligible resistance or zero resistance between those 2 points, the voltmeter will read 0 volts. So for there to be a reading on the voltmeter, there has to be a resistance between the 2 points that the voltmeter is connected. And always we connect the voltmeter in parallel. Ammeter is always connected in series. Now greater the resistance between the 2 points, greater will be the potential difference, because the greater will be the potential drop. Now anywhere from here to here the potential is 6 volts. Anywhere along this path, this wire, the potential is 6 volts. Now anywhere along this path from here all the way to here, it will be 0 volts. So what will happen is this 6 volt will drop by 2 volts when it when you go across this. So what will happen here, the potential will be 6 minus 2. Now how do I know it's 2? It's reading on the voltmeter. So 6 minus 2 is 4. Sorry, 6 minus 2 is 4. Now here it is 4, here it should drop to 0, because on this side it's the negative terminal, it's 0. So here you see 4, then you can see here is 4, so 4 minus 4 is 0. So you can see the greater the resistance, greater will be the potential drop, because the potential difference between on either end will be, if you take from either end, will be greater. Now one more thing, the resistance here is double the resistance here. So the potential difference across this will be double the potential difference across this. So the potential difference, if you have a loop like this, now you can see this is a loop, the potential difference will divide according to the ratio of the resistances. So here you can see the ratio is 20:10, which is 2:1. So that means the potential difference will also have the same ratio, which is 2:1. Now you can see here 4:2 means 2:1. Okay, now how is it 4 and 2 here? Because the total of this should be 6 volts. There is nothing else here. So when you add the potential differences, it should equal to the EMFs around that loop. That is called the Kirchhoff's second law. We will see this in the next video in part 2. So if you go around a loop, Kirchhoff's second law states that the sum of EMFs around a loop is equal to the sum of potential differences. Now you can see that the EMF is 6 in total, and 2 plus 4 is 6. So that is the Kirchhoff's second law. So there are several key points that you learned here. The potential difference will divide according to the ratio of the resistances in that loop. And here you can see the resistance here is double the resistance here, so the voltage here will be double the voltage here, and also the sum of the voltages around that loop should be equal to the sum of the EMFs, which is 6 volts here. In the circuit diagram of figure 6, the 2 voltmeters measure the potential difference in the circuit. Okay. The total potential difference across both resistors will be the sum of their individual potential differences. So the total is 2 volts plus 4 volts, which is 6 volts. So from here to here, you can see it's 6 volts. Now, so in series, the voltages add up if it's in a loop like this with a power supply. Then voltages in parallel circuits. Now, if the components are in parallel, they will have the same voltage across those components. Now see, this and this, they are all connected in parallel to each other. So the voltmeter here will read V1 equal to 6 volts. V2 will also be equal to 6 volts, because all three are connected in parallel to each other. So they will all have the same potential difference across them. So if components are connected in parallel, they will have the same potential difference. If components are connected in series, they will have the same current through them. If the total voltage across any branch of a circuit is known, then the voltage across any other branch in parallel with it will be identical. Both voltmeters here will read 6 volts. The voltage is the same across all parallel branches within a circuit. So this is what I explained just now. Now we will see resistance and how we can calculate the total resistance of resistors in series and parallel connection. It's very simple. You have, I think, seen this in the O-level IGCSE 9 to 1 AQA or OCR classes. Resistance can be calculated from Ohm's law. You have learned the Ohm's law. R is equal to V over I. If you rearrange, it will be V equals IR. This is a very important equation. That is the Ohm's law equation. V equals IR. When you rearrange, you get R equals V over I. So the voltage is proportional to the current, provided the resistance is constant. Resistance can be calculated from Ohm's law. This can be done for an individual component or whole branch of a circuit as long as the voltage and current are known. This also means that if we follow the rules for current and voltage variations around series and parallel circuits, we come up with simple rules for the total resistance in series and parallel connections. So we will see the details now. Alright, so first we will see resistors connected in series, and then we will see resistors connected in parallel and how to derive this equation. Very simple. So we know this equation, Ohm's law equation, R equals V over I. Now if you see figure F, that is A, B, C, D, E, F, this one. Okay. Now these two resistors are in series. So the total resistance, when they are in series, we simply add the individual resistances. So from here to here, the total resistance, which means it's the same as the total resistance in the circuit because there are only 2 resistors, the total resistance will be 10 plus 20, which is 30 ohms. So we add them like this. Any group of resistances that follow in series in a circuit with no junctions in the circuit will have a total resistance that is the sum of their individual values. In figure F, we could use the total potential difference across both resistors and the current through them to calculate the total resistance. So we know the equation R equals V over I. Then it is 6 divided by 0.2. Now how do we get that? 6 is the potential difference between this point and this point. That is 2 plus 4, 6. Also we can take it to be this. And then using the equation R equals V over I, Ohm's law equation, 6 divided by the current is 0.2. We get 30 ohms. And this is the simple way to do it. You can simply add the individual resistances to get the total resistance. Total resistance is also called combined resistance, effective resistance, equivalent resistance. There are several names to mean the same thing. Total resistance, combined resistance, effective resistance, equivalent resistance. 4 names to mean the same thing. Ammeters in series and voltmeters in parallel do not affect the total resistance and can be ignored. Now voltmeter has a very high resistance. We can say like an infinite resistance. So current doesn't flow through the voltmeter. So whatever current, now in this case the current goes like this. So whatever current that comes through this branch doesn't go this way. Instead it flows through the lamp. Because the voltmeter has a very high resistance, where a negligible amount of current flows through the voltmeter. Actually there is a current flow, otherwise it doesn't power the voltmeter, but it is a negligible amount. Similarly with the ammeter has a resistance, but it's a negligible resistance. So they don't contribute to the resistance in the circuit as a result. Because here we assume no current is flowing, so it's like not connecting this. So that's why even though it has a very high resistance, because current is not flowing through that path, we assume this resistance is not part of the main circuit. And that's what this means here. These do not, ammeters and voltmeters do not affect the total resistance in the circuit. Then how do we get this equation? The total resistance, also called equivalent resistance, effective resistance, combined resistance equation. When in series, this is the equation. We simply add the individual resistances to get the total resistance in the series connection. How we get it is like this. Now we saw that the total potential difference from here to here is simply the sum of the individual potential differences. So we can say the total potential difference is V1 plus V2 plus V3. Now if there was a third resistor in this series connection, it will be plus V3, but here there are only two, so we will have V1 plus V2. Now so it can be any number, V1 plus V2 plus V3 plus any number plus Vn. Let's say now for mathematics you would have learned series sequences and series, so we can also use that symbol. I will later write it in the notes and show you all after the recording. Okay, so we have this, then V equals IR, Ohm's law equation. Now here for this we can write I times the total resistance. So it's the same current because we are considering this point and this point. So from this point to this point there is no branch, no current flows through the voltmeter. So whatever current flows through this flows through that. So from here to here the current is the same as the current through the resistor, which has the total resistance as the resistance of these individual resistors. So when we find equivalent resistance, that's what it means. It's like replacing those resistors with a resistor which has the same resistance as both of them together. Then we have this. Then for V equals IR equation, R here for total voltage between those 2 points will be the I times the total resistance. Then for V1, the first resistor, it's I times R1, for the other one I2 R2, and here there are only two of them, so we can see the I is the same for all of them. So we have this. Now in the first case, that is what we have here, it's just R1 plus R2, so it doesn't end at R3. It can be any number. It can even go all the way to 100 R100. Resistors in parallel, this is the equation that we use to find the total resistance of the resistors that are connected in parallel like this. They are in parallel with each other and also parallel to the cell here. Now this part you might wonder, what is this? It's like this, but it doesn't look like it's the same thing, because from here to here it's just a wire. So wire has zero resistance. So you can imagine that this branch is brought all the way here. It can be drawn in different ways. This is one way. Same thing you can, I will just sketch it quickly. Same thing you can draw it like this. So like this, like that, like that. It's the same thing. Only thing is the wire is showing you a difference there. Okay, it's the same thing. So this diagram is exactly the same as this one, because this is just a wire. So instead of having the wire bending here, you can just straighten it out. When you straighten out the wire without having a bend here, and just this part is also wire, if you straighten it, and what you will get is this. Okay, so this is the formula that we use to find the total resistance when resistors are connected in parallel. Now remember, it's 1 over this, and in the end you have to take the reciprocal. A lot of students have noticed forget to take the reciprocal, not a lot, a certain number. Now how do we, let's do this. In the circuit diagram of figure H, which is this one, resistors in parallel follow reciprocal sum rule to find their total resistance, and the resistances are given here. What is the overall resistance of the block of 3 resistors? So we use the formula 1 over 16 plus 1 over 24 plus 1 over 48 is equal to 1 over the total resistance, also called equivalent resistance, effective resistance, combined resistance, yeah, those things. Then yeah, you can directly use the calculator and get the value, and remember to take the reciprocal in the end. So you can use the calculator from here onwards and directly you can get this answer. And remember, you have to take the reciprocal of both sides, or simply cross multiply, then you will get 8. If you are doing it without the calculator, you can find the LCM of these numbers, which is 48. So to get 48, you have to multiply both numerator and denominator here by 3, here numerator and denominator by 2, and here by 1. So then you get 3 to 1. Now the denominators are the same, they are like fractions, so you simply directly add the numerators. 3 plus 2 plus 1 is 6. 6 over 48. 6 times 8 is 48, so you get 1 over 8. You simplify this fraction to its simplest form, which is this, and then take the reciprocal on both sides, flip both sides, you get this. So the equivalent resistance of this is 8 ohms. Now remember, when resistors are connected in parallel, their total resistance is less than the resistance of the resistor with the least resistance in that parallel connection. So what that means is, if you look at the resistances here, it's 16, 24 and 8. Now the total resistance of this parallel connection here should be less than 16. And you can see that it is 8. Because 16 is the least value, it should be less than the least value for the total resistance in this parallel connection. Now, whereas when it is in series like this, the total resistance should be more than the resistor with the largest resistance. Now here you have just 2 resistors. The largest out of them is this 20 ohms. So when you find the total resistance of resistors connected in series, you add them. Because you add them, the total resistance of that series connection, equivalent resistance, will be greater than the largest one. In this case, it will be greater than 20, and you can see the total is 30. It's greater than 20. You can directly see that it should be greater because you are adding the individual resistances. So when in series, the total resistance is greater than the largest resistance of the resistor in that series connection. In parallel, it is less than the least value of the resistances in the parallel connection. That is a very important point. Make sure you remember that. Any combination of resistors in parallel will have a total resistance that is smaller than the smallest individual resistance in the group. This is what I explained just now. How do we get this equation? So let's see the derivation here. I told you the Kirchhoff's first law, which states that the sum of currents entering a junction is equal to the sum of currents leaving that junction. And also higher current will flow through the lesser resistance path. So the largest current that flows here is through this branch because it has the least resistance. Then the next higher amount of current will flow through this branch, and through this branch the least amount of current will flow. Okay, so that is what we are using here, the Kirchhoff's first law, which states that the sum of currents entering a junction is equal to the sum of currents leaving the same junction. So I total is the total current entering, that should be equal to the current here plus the current here plus the current here. So we can call this I1, I2, I3. We have that. Then you know the Ohm's law equation, V equals IR. We can make I the subject of the equation. Here we made V the subject of the equation earlier and used that here. Now that was when it was in series, when the resistors were in series. Here the resistors are in parallel, so we use this. Now the total current is V. Now V is the same for all of them, which is 240 volts because they are all in parallel. So when they are in parallel, they will have the same voltage or potential difference across them. So all these resistors have a potential difference of 240 volts, the same potential difference across them because they are in parallel. So we can say V divided by the total. Now we are using this. Okay, for this we write V over the total resistance is equal to I1 is V over R1 plus I2 is V over R2 plus I3 is V over R3. Okay, so V is the same, we can cancel it out, then we get this. So very simple. This is how we derive the equation for the total resistance of resistors connected in parallel. They have the same potential difference across them. We use the Ohm's law with the Kirchhoff's first law equation to do this. Now this is what we did when we had the resistors in series. They have the same current. So here we could cancel out the current. Here we cancelled out the potential difference or voltage. Okay, so you can have a connection like this with resistors in series and also in parallel. So you may need to find the total resistance between these 2 points. So what you do, you find the total resistance of these two and then add it to this. Here they are in parallel, so when they are the same, it is halving. If you have two resistors, you can actually use this equation and figure it out. Now see, So it will be 1 over R1 plus 1 over R2 for these two resistors because they are in parallel. And you can see since they have the same value, it's the same as 1 over 100 plus 1 over 100 kilo ohms, right? Then it will be 2 over 100. And when you take reciprocal of that, it will be 100 over 2, which is 50. So remember, if you have two resistors in parallel, then the total resistance will be half the value of one of them. Here it will be 50 ohms, here 50 kilo ohms, and then now this whole thing, the 50 kilo ohm equivalent resistor for these two resistors is in series with this. So when in series you add, so it will be 50 plus 100, which is 150 kilo ohms. You can see here they have done it here. Oh, okay, the working is also shown. So this is the working for this part which I verbally explained to you just now. You can see that 1 over 100 plus 1 over 100, which is equal to 2 over 100. Then 2 over 100, when you simplify, you get 1 over 50. Take the reciprocal. Remember to take the reciprocal. PARA means parallel because they are in parallel. So the total resistance of this parallel connection is 50 kilo ohms. Then for the whole circuit, the total resistance is 100 plus the 50 there, which is 150. So our total is 100 ohms plus the equivalent resistance for the parallel connection. Okay, this table summarizes what we went through so far. In series, the current is the same through the components which are in series. And in the current, if it's a parallel connection, the sum of currents entering a junction is equal to the sum of currents leaving a junction. Also any point in the circuit, if you take like this point, the total current entering this point should be equal to the total current leaving the point. So in some textbooks, you might see the Kirchhoff's first law stated as the total current entering a point is equal to the total current leaving a point. So point can be any point on the circuit. So here this is also a point. So total current entering this point should be equal to total current leaving the same point. That is this equation which we call the Kirchhoff's first law. Kirchhoff's second law we will see afterwards. I already explained to you anyway. Now looking at this table, voltage in series, we add the voltages of the components like what we saw over here in this diagram. So the total potential difference of voltage between these 2 points is the sum of the individual potential differences, also called voltages, which is 6 volts. 2 plus 4, 6. And that is what we have here. That is when it is in series. Now, if the components are connected in parallel, the voltage is the same across all those components. So voltage is the same on each branch when in parallel. Okay, so this column is for parallel, this column is for series. Then resistance, we use this equation to find the equivalent, also called total resistance, combined resistance, effective resistance. When in series we use this, when in parallel we use this equation. Remember, it's 1 over this, and remember to take the reciprocal in the end. Certain number of students forget to do that and simply they lose marks just for that simple mistake. Okay, so I think that's the end of part 1. Make sure you answer all these questions here and check the answers at in the answer script. That is very important that you do that. There is just one more here, investigating circuit rules. Make a complex circuit with various okay, so you can do this in the lab. We can also do it in the lab here. You can note these things down so that we can do them in the physics lab afterwards, after the pandemic. Okay, next we will see electrical circuit rules.